Okay, this lesson is kind of an introduction to what we're going to be talking about the next couple of days. So, we're going to discuss the difference between temperature and heat. We're going to talk about energy transfer, and we're going to do one quick practice problem to help us calculate the amount of energy released by an object. Just to kind of get us ready for the lab that we're going to do next. Well, so if I, this is a little thing we'll do in class, but you can probably just think through this. Or if you're at home and you have a spoon you want to go grab, if I held out a metal spoon and a plastic spoon and asked you to say which one is colder, and you felt them, you might would notice that the metal actually feels colder than the plastic spoon. And then if I asked you which one do you think would melt ice faster, you probably would guess the plastic spoon because it feels warmer, right? Which makes sense. And so in class, we're going to actually test this out. And what we're going to notice is that the ice actually melts faster in the metal spoon. So we're going to kind of talk about why that is, because that's not really what we would think would happen at first. So this all kind of comes back to heat transfer. And so when something feels cold to us, it's really because heat energy is kind of being transferred away from us, away from you. It's almost like it's pulling the heat energy out of your fingers, away from your body. If something feels hot, it's because that heat energy is actually transferring to you or into your fingers. So before we go any further, we need to just quickly make sure we understand the difference between temperature and heat. So when we say the word temperature, what we're actually describing is the movement of particles or the average kinetic energy of the particles. So we've talked about this, how when we increase the temperature, our particles move around faster, right? So that's really all temperature is just measuring how fast our particles are moving. So the higher the movement, the higher the kinetic energy, the higher the temperature. When we're talking about heat, we're talking specifically about the energy that moves between samples. And the reason that this energy moves between samples is because there's a difference in their temperature or a difference in how fast those particles are moving. One thing we also want to make sure we know is that because heat is a form of energy, we measure it in joules. So all energy is measured in joules. It's just a unit, just like we measure length in meters and mass in grams. We measure energy in joules. So when we talk about heat transfer, like what we were saying, something feels cold because that heat energy from your body is actually moving away from you. It's kind of getting pulled out of your fingers. Heat energy always moves from higher levels of energy to lower levels of energy, okay, or higher temps to lower temps. So if you ever heard your parents say, shut the door, you're going to let all the cold air out, that's actually backwards, because what's really happening is you're letting the hot air in, because that hot air, those particles are moving much faster, and so they're moving into the space where the lower temperature is, or the cooler air, or the slower the particles are. So if we look right here, we can see this, all of these particles, they're kind of this high temperature, they're moving around really fast. And so what happens is they kind of start colliding with these lower temperature particles, or these slower moving particles. And it's like a fast car hits a slow car. It kind of speeds up the slow car and slows down the fast car. So it kind of almost makes them start moving at the same speed, right? It's a little bit slower than the faster car was moving, but they're kind of both moving the same now. So that's what happens. So it causes that high temperature, or the warm substance, to cool down, and it causes the cooler substance to warm up. And so that's basically how the ice melts, is that heat from your hand is moving through the spoon, and it warms up the ice. We call this the thermal equilibrium. That's when both sides or both substances now have the same temperature, or the same amount of particle movement, because their energy is the same, right? Their kinetic energy is now the same, because our high energy is moved into our low energy area. So what does this have to do with spoons? Okay, so remember, you had 2 spoons, and you said you thought that the plastic spoon would actually melt the ice sooner. So you thought that the heat from your hand would travel through the plastic spoon and melt the ice quicker, when in reality that occurred with the metal spoon. So something about the metal spoon made it easier for that heat to travel, or made it better at allowing that energy to move from your hand to the ice. And that thing that makes it easier, right, for that energy to travel through is called specific heat. Okay, so there's kind of a complicated definition, and then I'll kind of explain an easier way to think about it. So here's the definition, okay? Specific heat is just the amount of heat energy required to raise the temperature of a substance by 1 degree Celsius. So the part about 1 degree Celsius, that's just kind of to standardize the measurement. But basically, it's just how much energy is needed in order to heat up or raise the temperature of an object. So we have some examples like in the chart. So here's water, ethanol. These have a high specific heat. So what that means is it requires a lot of energy in order to increase the temperature of that substance, or increase the movement of those particles. Okay, it requires a lot of energy to get those particles moving fast. Things like gold, silver, iron, those metals, it doesn't require a whole lot of energy to get those particles moving quickly. And that kind of makes sense, because if you think about it, if you like to cook, or if you ever set a metal spoon in like a cup of coffee or in a pot that's cooking, right? That metal spoon gets hot very fast. That's why you never want to leave it in there, because it's too hot to touch. But if I set a pot of water on the stove to boil, it takes a while for it to start boiling. It takes a while to increase that temperature. Okay, well, that's because the specific heat is high. It requires a lot more heat energy to actually get those particles moving quicker. Okay, so we should be able to answer this question. Why did the metal spoon cause the ice to melt quicker? Well, the metal spoon has a lower specific heat than the plastic spoon. So remember, the lower the specific heat, the less energy that's required in order to heat up a substance or raise the temperature. So on the back of your notes page, we're going to talk about how can we actually measure this heat energy transfer. So that's what our lab is going to be based on next. We call this calorimetry. It's basically just the process of measuring the amount of heat released and absorbed during a chemical reaction. So we have a little setup here. So usually we use water just because water is readily available and cheap and easy to use. Okay, and we know and the temperature that water exists ranges, is easy to read. So you have a container, okay? We call it some type of insulated box. We want it insulated because we don't want to let this energy that's being transferred or to escape. We want to kind of contain it so that we can measure it correctly. So inside this small box right here is where we have like our sample substance. So whatever it is that's going to be releasing our energy. And then we have it kind of inside this or surrounded by water. For our sake, it's actually going to be kind of like above the sample. Our water is going to be kind of above the sample, but and ideally it would be surrounded by water. And then we have a thermometer. That's how we can measure this temperature change. So what we would expect to see is that the energy located here in our sample is going to be released into the water. Okay. And as that energy moves into the water, right, it's going to start heating up the water. Let me rephrase. As the energy moves into the water, it's going to start causing those particles to move around quicker, right, because that energy is being transferred. And as the particles move faster, we know our temperature is going to go up. So we can kind of measure our temperature change and determine how much heat we have transferred in our system. So we have a formula that we use, and you have kind of this part is explained in the little dotted box in your notes. So if you forget it, or you don't have to rewrite it, it's already there. So the Q, that's just our energy. So Q stands for our energy. The M is the mass of the water, or like I said, it's usually water. It's kind of whatever you're talking about, like what you're measuring the temperature of, okay? And then we have our specific heat, okay? Remember, this is just that standard number. It's a constant. It's going to be, usually it's given to you, and it doesn't change. It's always the same per substance. It's not going to be, it's like that graph. It's not going to change depending on how much heat is transferred. Once you say the substance, it is what it is. And then we have our change in temperature. So this delta, this little triangle, that means change. Okay, so our temperature change. Remember, however much our thermometer's changing, that kind of lets us know, that energy is being transferred because it's causing those particles to move faster and increase the temperature. Okay, and we want to make sure that we're using degrees Celsius. We don't measure in Fahrenheit in science. Remember, we use the SI unit, which is Celsius. We'll talk about Kelvin later. So for this, we're just going to stick with Celsius. So let's look at a quick example problem. That way, you're kind of prepared for your lab the next day, tomorrow. So I have a potato chip. And I want to measure how much energy is going to be transferred from this potato chip. So or how much energy it contains, basically. This is a way we're going to burn it. So we're going to light it on fire. And that, as the fire, it's going to kind of cause, remember we talked about anything that's flammable, burning is a chemical reaction. And this reaction is going to release heat. And so we can actually measure how much heat that chip can release, and then we will calculate it, how much energy exactly using our formula. So let's go ahead first and write down our formula, MC delta T, okay? And I'm just going to start reading my paragraph and kind of filling in my equation. So it says, you burn a potato chip and measure the change in temperature using a calorimeter filled with 50 grams of water. So that's my mass. So I'm going to go ahead and write it down. And remember, I always want to write down exactly what's in the problem, because remember, those decimals are there for a reason. That showed my precision of my instrument, and this is where I'm going to determine my significant figures. So I don't want to skip any numbers. I'm going to write it exactly as I see it. Okay, and then it tells me the specific heat of water is 4.184. Okay. And then it tells me my temperature starts at 21.5 and it rises to 24.2. Okay, so I need to determine my delta T, my change in temperature. Okay, so I went, we don't care too much about, we don't want a negative number. It's just your temperature change. So we're always measuring the amount of energy released, essentially, or absorbed. It doesn't, the negative sign isn't really going to matter for our equation. So usually the way you do it is you take the final temperature minus the initial temperature. So we have 24.2 minus 21.5. And that is going to be 2.7 degrees Celsius. So I'll write that right in my formula. Okay. And then I'm just going to multiply. So as I type it in my calculator, I end up with 564.84. Remember, we measure in joules. Remember, I need to do significant figures. Okay, and my temperature here, which I really should have had a 0 at the end of this so I could maintain my significant figures. This is 3, 3, and 4. We don't use significant figures of these because these are like a constant value. We always use significant figures of our measurements that we're taking. So we have 4, 3, and 3. So that means my answer has to be in 3. So I'm going to round it like this. So I have 565 joules. That was my energy released from my potato chip. So joules doesn't really mean a whole lot to us. I mean, I could tell you something was 1,000 joules and you're like, how hot was that? I don't know. So we're going to convert it to something that we're kind of familiar with. So we're kind of familiar with calories. There's 2 different forms of calories. We have calories with a lowercase c, and we have calories with a capital C. The calorie with a capital C is what's listed on like your food nutrition labels. In calorie, it's just a unit of energy. So as you kind of can imagine, if you don't eat any calories throughout the day, you will be tired because you need that that energy, those units of energy. So let's see if we can convert our joules to calories using dimensional analysis. So let me refresh 565 joules. So that's what I started with. Okay, and I want to go to big capital C calories. So first I have to start here. 4, so I know joules is on the top. I need joules on the bottom. So that's 4.184, and that's equal to 1 lowercase calorie. And then since I have calories on the top, lowercase calories, I'm going to have lowercase calories on the bottom. And I know that that's 1,000 is equal to 1 uppercase calorie. So when I type this into a calculator, I'm just going to multiply the top, so 565 times 1 times 1, and I'm going to divide by 4.184 and divide by 1,000. Be careful when you're dividing. Make sure you divide by both of these. So if you're going to, like, if you want to multiply the whole bottom first and then divide by everything, that's fine. Or you can just make sure you hit the divide key. So I got 1.35 calories. Okay, and I maintain my significant figures here. I have 3 significant figures here, so I have 3 significant figures here. Okay, so that's teeny tiny amount of calories. If you think you're used to eating probably like a handful of chips, it's like 150 calories, right? That's not very much that you energy released from that chip there. And then we can also we can convert how many calories per gram that was. So what we'll do in the lab is we'll do this, and then we'll kind of see how close you were to the actual nutrition label. So if I want to do this, what I really want to know is calories per gram. So I'm just going to set it up. 0.135 calories over 0.67 grams. So when I divide 0.135 divided by 0.67, it comes out to be about 0.2 calories per gram. So not a whole lot of energy from that potato chip, right? You might find during the lab that some foods have more potato chips than others. I'm sorry, more energy than others, not more potato chips. All right, so we have we're going to do an exit flip in class. So if you're not in class, I suggest you practice these two calculations. That way you can be prepared for the lab